Good afternoon. I'm John Van Dyke, and I'd like to talk to you today about exploring many-body localization in quantum dot systems. The work I'll be describing was performed at Virginia Tech, where I'm a postdoc in the groups of Sophia Economou and Ed Barnes, and was done also in collaboration with them and with two graduate students, Bikun Lee and Ada Warren. The subject of this talk is also available as a recent publication in Physical Review B, as shown here on the slide. Before getting to many-body localization, it's perhaps helpful just to take a step back and look at where the concept of localization in general entered condensed matter physics. And as with many things, this began with Phil Anderson, in this case back in 1958, when Anderson realized that electronic wave functions in a disordered potential can become localized. This is for non-interacting electrons. In particular, it was found that in 1 and 2 dimensions, this will happen for an arbitrarily small or weak amount of disorder. So Anderson's original paper created a huge sort of subfield of research. And to show just sort of one example that's come more recently, in the following Phys Rev B work, the authors considered electrons, non-interacting electrons on hexagonal lattice, and found that if one applies only a weak amount of disorder, the resulting wave functions are spread throughout the system, whereas strong disorder tends to localize those electronic wave functions, as Anderson has said. But localization also extends much broader than just within the confines of solid-state physics. Similar behaviors have also been seen, for instance, in light and water waves and other sorts of systems. But there's a crucial question that Anderson wasn't able to fully address at the beginning and has taken a long time to understand more deeply, and that's the question of what happens with interactions. In particular, in the presence of interactions, can the localization phenomenon still survive? As I said, somewhat more recently, people have begun to start looking at how the effect of interactions has on localization. And since about 2005, many papers have been devoted to this subject. Here, I'm just giving a very short list of some relevant works. And the upshot of all of this work is that localization does indeed survive sufficiently weak interactions. And perhaps from an even broader point of view, this has been found that strongly disordered isolated quantum systems can actually fail to thermalize, basically providing a counterexample to the normal situation in conventional statistical mechanics. And a number of different signatures have been developed for diagnosing many-body localization, including, say, the level statistics for some exactly diagonalized system, which changes from so-called Wigner-Dyson statistics at weak disorder to Poissonian statistics at large disorder, shown in this plot. Another useful signature is the time evolution of the entanglement entropy of a system, which is found to have a regime which scales basically logarithmically with the time, thereby showing a rather slow development of correlations in a many-body localized system. MBL systems are also very interesting from an experimental point of view. There's been a number of different realizations which have seen indications of MBL behavior, such as, say, trapped ion experiments or cold atoms, and also in superconducting qubits. And one of the things that, of course, unites all these different systems here is that these are all leading platforms for quantum computing, which makes a lot of sense because in order to see many-body localization, one needs to have very well isolated systems, which is also important for these computing ideas. So it's this combination of isolation from the environment plus a large degree of tunability, for instance, over interactions in the system, that makes quantum computing platforms also ideal testbeds for MBL physics. So this naturally raises the question of, can we also observe MBL in other systems that are interesting from a quantum computing point of view, in particular, systems of spin qubits? And that's what I'd like to focus on today. In particular, looking at gate-defined quantum dot arrays that can host spin qubits, these have a number of interesting features that are useful for studying MBL. First off, they have tunable Heisenberg exchange interactions, which would hopefully allow one to go from the disordered, weak disordered limit of ergodic systems to the strong disordered many-body localized side fairly easily. They also have an inherent amount, at least in some cases, of magnetic field noise, for instance, in gallium arsenide due to a nuclear spin bath. And finally, they have a great deal of control, which can be obtained through an embedded micromagnet, allowing for single site addressability in such an array. And these embedded micromagnets are especially interesting because essentially the way that they work is that they provide a magnetic field gradient, say for a Heisenberg coupled quantum spin chain. And this, in fact, has been recently understood to provide an alternate route to localization, which I'll discuss now. So going back a number of years, there's a concept of so-called Wannier-Stark localization, which occurs when you have electrons that are subject to a strong electric field. The wave functions can become localized even in the absence of disorder. So this case of, say, spinless fermions in an electric field can be mapped via a Jordan-Wigner transformation to spins in a magnetic field, or gradient. And this provides, furthermore, signatures have been found studying such a model that are in close agreement with those found from disorder-based MBL systems. For instance, the level statistics and the logarithmic growth of entanglement entropy is quite similar. Now, this of course raises the question, are there additional signatures that one can find, and especially ones that would be useful for experiments? So we've set out to investigate this question, and one idea that we've had was to basically look at the so-called quantum Fisher information as a possible signature of MBL. Now, the quantum Fisher information for a pure state has a simple form. Given an operator, Hermitian operator O, and some wave function, the quantum Fisher information is simply the variance of the operator. And in a general sense, the QFI measures the sensitivity of a given state under unitary evolution generated by the given operator. And furthermore, it witnesses entanglement when its normalized value exceeds 1. So this quantity was already considered as a possible probe of MBL physics. For instance, in the 2016 paper of Smith et al., where they used it to diagnose the presence of many-body localization behavior in a trapped ion system. In particular, they're able to show a logarithmic growth of the entanglement through this measurement of the quantum Fisher information. Now, this experiment that was performed is somewhat different than what would happen in a quantum dot chain. Namely, it involved Ising model type system with long-range interactions. However, we wanted to take the same idea and explore what happens, say, in a Heisenberg model appropriate for quantum dots, with the inclusion of a magnetic field gradient in addition to some disordered magnetic field. So we performed this calculation, and we found that the value for the quantum Fisher information strongly depends on the strength of the magnetic field gradient, which is present in the system. In particular, there's a very strong suppression in the late time value of the QFI with increasing field gradient. And plotting this as a sort of phase diagram with disorder on the x-axis and gradient on the y-axis, one can see that at low gradient and or disorder, the system has a very large value of the QFI consistent with a reasonable amount of entanglement in the system. Whereas at either large disorder or large gradient, the QFI is highly suppressed, indicative of localization. Furthermore, if we look at the quantum Fisher information versus the magnetic field gradient, we see that there's a simple relation present at the late time value of this quantity. Namely, it has an asymptotic J squared over G squared type dependence, where G is the magnetic field gradient, again, sort of independent of the amount of disorder in the system for large gradient. And this particular form of the asymptotic dependence, we were able to understand by using a perturbative Schrieffer-Wolff type transformation to show the leading order terms in the quantum Fisher information expansion. Another signature that we considered is that of heating of the system due to some periodic driving. And this particular diagnostic was considered for both ergodic and then later for MBL type systems back in 2015, first in Ponte et al. And they in particular calculated basically a normalized value of the energy of the system, which they called Q of T, which essentially takes the value 1 if the system heats up to infinite temperature and remains close to 0 if the final value of the energy of the system is very close to the initial value. So we also calculated this normalized energy quantity Q for the gradient field Heisenberg model. And we found signatures that are very consistent with what we found also with the quantum Fisher information. Namely, at small gradient and disorder, the system heats up eventually to infinite temperature, consistent with ergodic type behavior, whereas the presence of a sufficiently large field gradient causes the system to essentially never heat up as a function of time. Furthermore, by looking at the bottom panel here, one sees that this localization type behavior does not appear to be pre-thermalization, because as we consider in the different colored lines, further out times at which to probe the normalized energy, we see that for large gradient, going out to later times has very little effect on the final value of the normalized energy. Whereas in the case of pre-thermalization, one would expect that the system would eventually heat up to infinite temperature, which is not the case here. Thus, to summarize, magnetic field gradients provide an interesting alternative route to many body localization than the typical disorder-based approach. And in particular, gate-find quantum dot arrays are a realistic platform for obtaining MBL experimentally. In particular, there's two interesting probes that we've considered for diagnosing such behavior, such as the quantum Fisher information and heating of the system under periodic driving. And in the talk by Bi-Kun Lee, he will discuss further signatures that we discovered that these gradient field Heisenberg models can also host discrete time crystal phases. Thank you very much.